This is Math 251, and we're looking at section 14.7 right now. Actually, the last two sections of this chapter are going to study two very famous theorems. One is called Stokes Theorem, which we'll study here, and then in the next section we'll be looking at the divergence theorem. These two theorems are actually the three-dimensional versions of the two forms of Green's theorem. So we'll be three-dimensionalizing those famous theorems. First of all, in this section, Stokes' theorem is the three-dimensional version of the circulation form of Green's theorem. And I'd like to start by just quickly reviewing with you what Green's theorem said for the circulation form. Two-dimensionally, I had a vector field, F, defined as Fg. R was a region in two space, bounded by a closed curve C. And we then said our circulation, f dot TDS, over that closed curve, could be calculated as the double integral over the region R of partial of g with respect to x minus partial of f with respect to y dA. This thing, we actually gave it a name. We called it the two-dimensional curl because we had not yet studied curl in general, so we didn't have a three-dimensional version. So it was really just the double integral over R of the curl of f dA. We looked at this kind of in terms of a picture by saying if we have this closed curve C, and this did have to be traversed counterclockwise, which I neglected to say there, and that closed curve then contains a region R, then the circulation on the boundary was determined by the curl in the interior. And we even talked about that a little bit, about why that kind of made sense. Curl essentially measures how much our vector field is swirling. It's a tendency to swirl. And so if we've got a lot of swirl in here, again, it's kind of like that current in the swimming pool, right? The swirl inside creates a current that pulls you around the outside edge. All right, how are we going to three-dimensionalize that? Well, to do that, we get this theorem called Stokes' theorem. We're going to now have a three-dimensional vector field. And S is not just a two-dimensional piece, but it's a three-dimensional surface, not a two-dimensional region, but a three-dimensional surface in three space, bounded by the closed curve C. So if I were to just think about that so far, if I've got some curve C, and again, I am going to imagine that I'm going around this counterclockwise. Let's imagine that that closed curve C is the boundary not just of some flat two-dimensional region, but of some three-dimensional surface, S. What does Stokes' theorem say? It says that our circulation, f dot TDS, so the circulation around C, can be calculated as the double integral not over the flat region, but over the three-dimensional surface now of the curl of f dot n ds. Since we are integrating over a surface, we have the d capital S. This is a surface integral. And to do surface integrals, as we studied in the last section, it's the curl, or excuse me, we have to take whatever we're working with, dot n ds. Notice here we use the curl for the same reason we used the curl up here. This f dot t became the curl of f dot n. So it's exactly analogous to that two-dimensional Green's theorem. It's just now been three-dimensionalized, and we're allowed to integrate over a surface, not just a flat region. Now we know how to calculate this. That's what we were doing in section 14.6. We calculate this surface integral by taking the curl, which is the gradient cross f, dot n ds. And the way we did this in the last section is we took our function that we're integrating, in this case the curl, dot little n dA, where remember, n was the gradient of W, and for W, we'll use z minus z of x and y equals 0, making that a level surface. I'll always subtract it this way. If I'm traveling counterclockwise, that will guarantee me I'm in the right direction. Oops, and I'm sorry, I went slightly off the page. Let me just move that up a little bit so you can see what I just finished writing there. So again, we take our curl, gradient cross f, dot it with little n dA, little n being the gradient of W, just like it was in section 14.6, where we defined our W as z minus z of x and y, equaling 0. Because it's 0, it is a level surface. Traveling counterclockwise, if I always subtract in this direction, I'll have the correct normal vector that I need to get the circulation. All right, so let's take a look at our first example. We want to find the circulation for f is equal to minus y minus x minus z and y minus x. On the path C, C is the slanted ellipse that forms the boundary of the part of the plane, z equals 6 minus y, that lies inside the cylinder, x squared plus y squared equals 16. We're being asked to do this problem two ways. First of all, using a line integral, just the method that we would have used before Stokes Theorem, and then we'll use it again, or we'll do it again rather, using Stokes Theorem. So let's go ahead and I'm going to start using our familiar method, and then we'll go back and try the new method with Stokes Theorem. So, using the old-fashioned way, parameterization. First of all, what does this thing look like? Well, let's see here. We have to be inside this cylinder of radius 4. So let me just sketch the cylinder first. And then I want the plane z equals 6 minus y cutting through that. So let's see, if this is 6 here on the z-axis, it would have a slope of -1, so it's going to kind of slant through and cut through like this. And I'm just going to draw the intersection. I'm going to end up with this slanted ellipse. So this is my curve C. And I want the circulation as I go around counterclockwise around that curve C. All right, if I'm going to parameterize, then my first job is going to be to parameterize C. And since C is above the circle of radius 4, I can use 4 cosine t and 4 sine t as my x and y. And then z is 6 minus y. Notice I've already defined x and y here. So when I go to define z, I'll have 6 minus, and then I'll put in for y the 4 sine t. All right, I need r prime. So -4 sine t, 4 cosine t, and -4 cosine t. And then I need f. Minus y would be -4 cos t. Negative x minus z. So let's see, negative x would be a positive 4 sine t. Subtract z. Oops, I'm sorry, I got that one wrong. I apologize there. Let me start f over. I was using the r primes rather than the r's. I'll redo my f here. Minus y. Here's y up here. So minus y would be negative 4 sine t. And then the opposite of x, so minus 4 cosine t, minus z. So if I subtract z, that'll be a minus 6 and a plus 4 sine t. And then finally y minus x, 4 sine t minus 4 cos t. All right. So my circulation is going to be the integral of going all the way around, so 0 to 2 pi of f dot r prime dt and so I've got my f dot product with this r prime dt. All right, again, I think I gave us a blank page to work because this is a long problem, so let me shift a little bit here. All right, so here we go. We're going to evaluate our integral. So I've got to do that dot product. And I'm going to get 16 sine squared t and then I'll get a negative 16 cos squared t a negative 24 cos t and a positive 16 sine t cos t. And then over here I've got a negative 16 sine t cos t and then a positive 16 cos squared t. And let's see, it looks like we can get rid of some stuff. Those will go. Those will go. So really, I just end up integrating 16 sine squared t minus 24 cosine t from 0 to 2 pi. And I did that on the calculator and ended up with 16 pi. So by our traditional parameterization method, that circulation turns out to be 16 pi. We now want to take a look at this using Stokes theorem. Of course, we should get the same answer. But let's see how that works. First of all, notice that Stokes theorem applies. In order to use Stokes theorem, I have to have a closed curve, and I have to make my curve encloses some surface. So in this case, my curve C encloses the surface S, and S, if I take a look again, S was this plane, Z equals 6 minus Y, within the curve C. So this is our S in here. R is the projection down into the XY plane. So R is going to be this circle of radius 4 down here. And according to Stokes' theorem, I'm going to go right to here. what I need to do to calculate my circulation is to take the curl, gradient cross f, dotted with n, where n is the gradient of w. So let's go ahead and write a couple of things down here. Again, S was, in this case, the piece of the plane. Z equals 6 minus y. So I'm going to go ahead and get the n right now. Let's see. To get w, I take z minus z of x and y. So z minus 6 plus y equals 0 becomes my w, and n is the gradient of w. Let's see, gradient of w in this case would be 0 with respect to x, 1 with respect to y, and 1 with respect to z. So there's our normal vector n. I'm going to dot product that with the curl of f. So the next thing I need to calculate is curl f. F, for this problem, was right here. I'm just going to jot it down. Minus y, minus x minus z, y minus x. And I need the curl of f. Which is the gradient vector, or the gradient operator, cross product with f. So let's see, there's my gradient operator, and I'll put f in this last line. So, and let's see here, doing the main diagonals to get our curl, we would have 1i, 0 j's, and then negative 1k. Subtract, go the other direction here. Let's see, that'll be a negative 1k. And that's a negative 1i. And that would be a negative 1j. So I have what does that give me? 2i plus j? Or 210 for my curl. All right, we mostly have what we need here. We've got our n vector, we've got our curl vector. So one more time, Stokes Theorem says take the curl dotted with n and integrate over the region R. So I'm going to take the dot product of those two vectors we just found, and I'm going to integrate them over this circle of radius 4. Just a reminder that, again, R was a circle of radius 4. All right, so our circulation, double integral over this circle, and I'll go polar, so r goes from 0 to 4, theta from 0 to 2 pi, of the curl vector, 210, dotted with the n vector, 0, 1, 1. And oops, this is polar, so it's r dr d theta for the dA. All right, finally, we got it all put together. Let's do the integral. That dot product is going to be 0 plus 1 times 1 is 1 plus 0, r dr d theta. Looks like the theta trick's going to work just fine, so I'm going to pull down the 2 pi, and then I just have the integral from 0 to 4 of r dr. Integrating that's just going to give me 1/2 r squared from 0 to 4. So I'm going to get pi times 4 squared is 16 minus 0, and there's that 16 pi again. So certainly Stokes' theorem gave us the same answer as the parameterization method. They're both equally valid. And what we'll look at next is why sometimes Stokes' theorem can be a real time saver. In this case, I would say it was probably about the same amount of work as parameterization, but there are times when it can be really valuable and help us get the answer much more quickly. All right, so to wrap up this section, we'll look here at example 2. We want to find the circulation of the vector field f, x squared minus y squared, z squared minus x squared, y squared minus z squared, on the curve C, where C is the boundary of the square that lies in the plane z equals 3, where the absolute value of x is less than or equal to 1, and the absolute value of y is less than or equal to 1. Notice that's just sort of a shortcut way of saying x is between -1 and 1, and y is also between -1 and 1. So let's see what we've got going on here. I'm up here in the plane z equals 3, and then I'm going to go, y goes from -1 to 1, and so does x. So I'm going to form sort of a square right around that point 3 on the z-axis. This is 1 to -1 on the x, and that was from -1 to 1 on the y. We'll assume, again, I sometimes don't remember to say it, but unless I specify otherwise, assume that we're always going counterclockwise. So that would be our path, or our curve C, all up there in the plane z equals 3. And we want the circulation as we go around that path for this vector field. How much help are we getting from that vector field as we go around that path? Now, here's where Stokes' theorem is really handy. We do have a closed curve, so we can use Stokes' theorem. Again, just like Green's theorem, Stokes' theorem requires a closed curve, and we have one. To do this one by the parameterization method, I would have to parameterize 4 separate curves. These 4 sides all have different equations. So this one would be kind of a pain in the neck to do using the traditional parameterization method. I think this one's definitely going to be faster with Stokes' theorem, where I can do this as a single surface integral instead. Right? So again, what we need, as a reminder, is the double integral over r of the curl of f, dot product with the n, dA. That's what Stokes' theorem says. In this case, for r, if I come out of the plane z equals 3, I've just got this square from -1 to 1 on both the x and y axes. So r is fairly easy to visualize. And so what I need to do is figure out the curl of f, and then I need to figure out the n. So curl f is our gradient vector cross product with f. Gradient vector, the partial derivatives, and the vector field, All right, there we go, long setup. So, doing our main diagonals first. Let's see, that's going to be a 2yi, and then a 0j, and then a negative 2xk. Subtract. We'll do the opposite diagonals. That's going to give me a negative 2yk. And let's see here, this one's going to give me a 2zi. And that's going to be a 0 for the j. So it looks like I've got 2yi minus 2xk plus 2yk minus 2zi. Or my first coordinate will be 2y minus 2z. And my second coordinate will be negative 2x plus 2y. Oh, excuse me. That's the k. I missed a 0 for the y, and all right, there's no j's, so sneak a 0 in there for the j coordinate. All right, so there's the curl. Next, we need the normal vector. Again, remember the surface is actually, pull this down one more time, the surface S is actually this plane z equals 3. And so to get W, I'm going to take z and subtract the 3 to get it equal to 0, meaning it's a level surface. And then my normal vector is just the gradient of W. So that's a real simple one this time. 0 with respect to x, 0 with respect to y, and just 1 with respect to z. All right, finally we're ready to set up our circulation integral. So I take the double integral over my region, and I keep moving things over. You can't see them, sorry. My region here went from negative 1 to 1 on both the x and y axes, so oops, it's positive 1. And then I'm going to take the curl vector dot product with the normal vector, dx dy or dy dx, it doesn't really matter since the limits of integration are constant, so they're identical. And then it's just a matter of doing our integration. Let's see, that'll be a 0 there, plus a 0 there, plus a negative 2x plus 2y. Integrating with respect to y will give me a negative 2xy plus y squared. And let's see. Plugging in y equals 1 is going to give me negative 2x plus 1. Subtract. Plugging in y equals negative 1 would make that a positive 2x plus 1. We're almost there. Let's see, that'll give me a negative 4x. And 1 minus 1 is just 0. So I've got a negative 2x squared from negative 1 to 1, which would be negative 2 times 1, subtract negative 2 times 1. And I therefore get 0 for my circulation on that square path. All right, that brings us to the end of section 14.7.